All right, folks. I thought I would record myself going through that because this is difficult and I'm not sure how FHE works. This is, by the way, I'm on page 11. All right. This is, there's a bunch of resources. I thought this looked amazing. TFHE-rs Practical Handbook. And I'm trying to sort of speed run through understanding some of the FHE, fully homomorphic encryption concepts. And this handbook looks pretty good. TFHE is the scheme that I guess the main companies doing FHE are using. I don't know exactly who invented it. I don't have that much background in FHE, but it's fully homomorphic encryption scheme where you can operate on like unbounded circuits because you're constantly reducing the noise by bootstrapping. So what's interesting, what the first thing I wanted to check, and I didn't really read too much about it, but there's different types of or there's different problems. We don't care, but there's different type of ciphertext. So that's what I'm looking into right now. So LWE ciphertext. LWE ciphertext, my understanding is that it's a secret key. How do you do public key encryption then if it's a secret key? And there's this mask. Whenever you encrypt something, I think you have to sample this mask so that you do an inner product between your key and this mask, and then you add that to your message, and then you add an error. And this is uniformly, they say it's uniform distribution, but the error is error distribution key, and that seems very different. And because you're sampling A, you're gonna belong to some sets of possible encryption of M, I guess, even though you have a fixed key. And I guess we're in a ring, not necessarily a field, because Q is not necessarily a prime. So it's basically the same thing as what we're looking, except that all the elements are in, they're not in ZQ anymore. They're in this RQ, which I guess is a ring as well. We have a polynomial ring quotiented by some polynomial that might not be irreducible. Since n is a power, I'm not sure. Where is RQN defined? just a polynomial quotient ring. Yeah. It's always like that. We're sort of abusing notation, I guess, and always calling them polynomials. Also, every element is a polynomial here, as 0 is a polynomial. Blah, blah. There's specific polynomial, right, defining this polynomial quotient ring, but you can see them as polynomial, I guess, when we define them, when we implement them. We skew the modulus in that polynomial and the degree. Or the max degree. So n minus 1 would be the degree of all these polynomials. That's what I'm saying. This is exactly the same, except that we have, I guess, what is k here? Right. So if the secret key is the same size as in definition 3, and these elements are in this polynomial ring, but they're all of degree 1, so it's just degree 0 basically. So n equal 1, meaning that elements here are gonna be of degree 0, polynomial of degree 0. They're basically constant terms, and that's basically back to the definition 3, where we just had element in that ring, like all the numbers from 0 to q. And constant term in these polynomials in this polynomial quotient ring are basically in the ZQ ring. It's good to understand these kind of things to wrap your head around it, I guess. Okay, so LWE versus GLWE. Okay. So we're moving to GLWE by using polynomial rings, basically, or polynomial quotient rings. So usually you do that because you want more security, I think. Your elements are bigger. You still have the same number of elements, but your elements are bigger because they're not just a number from 0 to q, but they're like polynomials created with these numbers. So you can see them as vector of such numbers instead of just having these numbers. So you're just increasing the number of parameters. Yeah, so the A's are the mask. Yeah. And the reminder, which is really the encryption, this one thing is the body. The message plus some noise plus the inner products between the mask and the secret key. All right, so you're deriving the mask deterministically, I guess. So that's a way to compress the mask. You just have a seed and you derive, you hash that seed or whatever. So remarks. Okay, maybe we can skip the remarks. We're speedrunning, right? All right, so how do we decrypt? Yeah. And then how do you remove the error? So this is the definition, right? This is just definition of how things, like the body is literally that message, the message plus the error plus the inner product of the secret key and the mask. So sure. Okay, let's just jump to the decryption. Algorithmic, sure. Return M, that's it? That doesn't sound like enough. Always do things fast. So they don't really explain how to decrypt, right? They don't explain how to remove the noise so far. Maybe explain that earlier, I don't know. Okay, how does someone encrypt without knowing the private key? Wait, they know the private key. So I thought it was a public key encryption scheme. Let's look at this public key. All right, there's different ways of doing FHE, right? So you either encrypt your stuff, you give it someone, they can operate on that, give it back to you, you decrypt it. Or what we see in the blockchain world now is there's some public key that no one knows the private key of, and so you can encrypt to it, and then the network can operate on it. And if you need to decrypt it, the network can threshold decrypt. So there's a committee, and they have shards of the private key, and they can compute that MPC to decrypt a ciphertext. And so in this case, you need a public key encryption scheme. So there's different types of FHE, right? Must be, right? What? Isn't that trivial to decrypt if you do something like this? That works though. Trivial encrypted, I guess you can easily decrypt them. Or this is useful when you have a circuit and you're trying to add, part of your circuit is to add the encryption of something you don't know plus 3, right? So you have to encrypt that 3 so that you can add them together. So you just need a trivial encryption. You don't care if it's decryptable, I'm guessing. So you, oh, and in this case, you don't even need to mask it, I guess, because you don't care if it's decryptable. Right. So you zero the key and the encryption just becomes message plus error. I guess you don't even care about adding an error. Is that what they're saying? Yeah, the noise polynomial is set to 0. It's not secure as there is no encryption, right? But we don't care because it's public values. I mean, simplified notation, or yeah, I don't know. We'll see. Let's keep going. Let's keep going. Yeah, key switching is gonna be interesting. I think this is how bootstrapping works. GLWE, there's a new one. So it's just a tuple. That's it, right? Yeah. Except we're multiplying with this constant, right? It's a constant. It makes me think of like RWE, LWE, like, so you're in a ring if you have polynomials of, you use polynomials, and then you're in a module if you use vectors, so if k is greater than 1. And so GLWE is basically modules, maybe, RW, R, or GLWE is modules. RLWE is just ring, and LWE is just in ZQ, I guess. That's the way they define things. I don't know why we need these. It's just weird, but all right. Didn't we define that one? GLW. Oh yeah, GGSW ciphertext. So many definitions. Bootstrapping key. All right. Tuple of GLF, which is a tuple of GLWE. Because it's a tuple again, right? It's just a tuple. So GGSW ciphertext is a tuple of GLWE ciphertexts. But we're encrypting these. And these GLWE ciphertexts are tuples, as we've seen. It's just -1. That's weird. So same thing, right? GSW, but you add like an R or a G. R for polynomial quotient ring, and G for just the vector of that. Right? All right. I like convention. I hate configuration, even in papers. You know, like in paper, convention over configuration is good in coding, but like you see these papers was like they define these things was like a million parameters, and then they only instantiate them in some ways, and you have to remember you know, like adversary of P rho alpha beta blah blah blah, and then instantiate that, and you have no idea in what order, like which one were these elements. It's kind of like having a function with a million arguments. Anyway, I'm taking a tangent. I need to get back to what I'm trying to do here. I'm not sure exactly, but let's pass. It's a piece of the puzzle. So yeah, that's that delta is a padding. At least in their other material. And we're now reaching the even with the maximum value, right, of a message modulus, right? Even with the maximum message value shifted, we still don't reach the we still don't reach Q, especially if you use P-1, not P. But you can reach it. You can reach the last, the maximum authorized value. So that's interesting. There's no leeway there. This rounding. I hate whenever we round. It complicates everything. What is this encode function? Okay, that's the encode function. I should read things. The plaintext modulus, okay. This is the plaintext modulus. Right, because after padding, it shouldn't reach that. That should be the maximum value. Oh, yeah, and we know that Q is divisible by 2 pi times P, right? I don't remember. So obviously we shifted, the value was here, we shifted it all the way here so that we can add an error without impacting the bits of the value we shifted. Wait, so P is the size of the modulus? We can only encode 4-bit values? Is that what's happening? Yeah. I don't have good intuition for what's happening here. Why, if we define delta by Q divided by that, it gets us all the way here. Yeah, I'm not sure. I really don't like that they're doing. Don't you like? It's always like that, right? In cryptography, you don't want to round because you're losing information when you do that. So that's interesting. I don't understand anything, but I'm still reading it. Sure. Use a probability. I guess we're gonna track these in order to know when we have to bootstrap eventually. Like we're adding noise all the time when we operate, and we need to track the maximal theoretical noise, and when the probability of decrypting is too low, then it's getting dangerous, or before it gets dangerous, then you bootstrap. I'm not sure. I think nega cyclics when you have a quotient that x squared plus 1 instead of x squared minus 1, because an x squared plus 1 xn plus 1 equals 0 means that xn equals minus 1 when you're trying to do the modular reduction when you're operating with these polynomials. What? Not sure I understand this. Footnotes to a remark. All right, I'm getting distracted. Right, because when we're gonna add, multiply, blah blah blah, the message is gonna increase size, right? So if the message takes all the room here, there's no room for carries in when we add or multiply. So we need the message to be even smaller so that we operate on it, the carry. So I guess the error can increase, that's bad, but also the carry can increase it, that's bad as well. You have to reduce stuff. Is that what's gonna happen? We're gonna have to do modular reductions on the message as well. Wow, so once the carry space is full, you need to perform a programmable bootstrapping. So you need, bootstrap is not just to reduce the error, it's also to reduce the carry. So that really sucks. You have to bootstrap all the time. Right, when computing linear operations, the error doesn't increase like crazy. So you just scale the error, or you add errors instead of multiplying errors. So things don't blow up like crazy, and so you don't want to have to bootstrap. Like, I guess you don't need to bootstrap, but if you don't have a big carry, then you do have to bootstrap. That's my read here. That's my read. My understanding is PBS, programmable bootstrap, or bootstrapping in general is expensive. You really want to like delay it as much as you can, or make it super cheap. I don't know how it works. So okay, so now we're talking about encoding. Do we need, maybe we can skip that simple operation. Maybe that will be useful. Okay. To remember, RLWE is just an inner product between a mask and a secret plus a message plus an error, and everything is just in a ring. And GLWE is like every element is a vector of polynomial quotient ring elements. I don't know why we were reducing to an RLWE ciphertext, but I guess this is how we can do a public key encryption scheme. Cool. All right, addition is always easy. You just add, right? Coordinate-wise addition, yeah. So it's always easy. Addition is always easy. The resulting noise will be the sum of two noises, yeah. Doesn't grow too much. What does it do? For the length of the vector, you just add the elements in the vector, yeah. So these are just the mask. A1 is the first mask, A2 is the second mask, so you get A3. You do that for every element in A. You add the body as well, and this is, yeah, it's fairly straightforward. I like to spend time on easy stuff, but you know, unfortunately, you have to spend time on hard stuff and really go through the easy stuff as fast as you can. And go slow when it's difficult. So here I should go slow a bit more because I'm not sure what's happening. So yeah, I guess they're they're saying if E1 and E2 followed a centered Gaussian distribution, whatever, then the new noise also follow a centered Gaussian distribution, and then they give you exactly how to write it. I don't know what that means. I must have learned that at some point. I'm always kind of lost when I go back to these things. It's not important. Not now. Algorithm complexity. This we can just ignore. Oh, yeah, bootstrapping operation is supposed to lower the noise now. Yeah, you're gonna public like this trivial encryption that we saw without encrypting noise. Sure, blah blah. All right, let's keep that. Rotation. That's weird. Power of X. Wait, what? What is... Why would we do that? X is an unknown. Oh no, X is not an unknown, right? It's just this is how we define our elements. We define them as polynomials. And so X is like the unit to create our elements. We're dealing with polynomials, but as objects, not as like things we can evaluate here. This is what's hard about thinking like that. But anyway, sure, the rotation is just that you multiply a power of X to the mask, to the body, and that's it. And it becomes an... oh, it's is that true? It's kind of weird. The output is exactly what would have happened if you encrypted the power of X to the message in the first place. That feels weird to me, because if we had done that, we would still have a normal mask, wouldn't we? Wait, the body is... oh, so that's interesting. Isn't there an issue here? Shouldn't this be X to minus W so that it can cancel... oh no, okay. So the body, when we multiply X to the body, we get X omega times the message, the error, and also the inner product. And so when we're going to want to cancel the inner product, we're going to have to cancel X to omega of the inner product. So that's correct. But the error is also going to increase by X omega. See, I just keep that part because I didn't understand it. Just my brain did it, but I need to force myself to read it. Here, symmetric means that... I don't understand what they're trying to write here. Okay, I must come back to that, but it's good to know. And sometimes, all these things are in the notations in the very beginning, but it's not fun to go through notations. So it's like watching Memento and these movies where you start by, things are... the story is spaced out. You see elements of the story, no order whatsoever, and it's so much more fun. And then at the end, you sort of piece everything together, and the story makes sense. If you haven't watched Memento, you should watch it. And so that's a good way to start reading paper. You start reading in the middle, you start reading in the end, you go here and there, you take a very weird route, but at least it's entertaining. You don't get bored by going through pages of notation. But you have to be entertained by what you don't understand as well, right? Let's be entertained by that paragraph. The rotation of CT in as the first ciphertext. So that's what I was saying earlier. The noise is also multiplied by that power. It's kind of hard to understand. It's like each coefficient of the noise in that ciphertext, because remember this is a vector, right? We're in GWE, so it's a vector of RLWE elements. Sorry, it's not a this is not a vector actually. It is a vector of size 1. So it's an RLWE of size 1. And each coefficient is in LWE. So it's in ZQ, right? Mhm. Actually, I might be wrong. This might still be a vector. It's confusing. Yeah, I think this is still a vector of polynomial quotient ring elements. So not only this has entries, these entries have coefficients because they're seen as polynomial, right? I don't know. Yeah, xn equals -1, so x2n equals 1, sure. Oh, okay. So that's how we only defined addition. We're gonna do the scalar multiplication, but I'm not sure I understand how they're doing this. So you have a ciphertext and you want to scale it by this element, right? What? Wouldn't you want to scale it? The message is in the polynomial quotient ring, right? Right? A vector in the of entries in the polynomial quotient ring. So why is the in just that normal polynomial ring? That's kind of weird. And you can just multiply things. There's no rotation anymore. I thought we were going to do the power of x stuff. Am I missing something? All right, let's continue reading because I'm confused. We don't care about implementation detail. All right, because they say the noise is yeah. I still don't understand. They said that. All right, they say that. So like, how are we combining them? Like we. Oh, I think I understand what's happening here, but there's no addition, right? Oh no, no. Okay, so this multiplication by d, where d is a, basically a polynomial, you can say that d is x to the power 0, yeah, x to the power 0 times, times the trivial encryption of something, which you've seen here, plus x to the 1 times the trivial encryption of something else, blah, blah, blah. And that gives us a d that's a polynomial. But of course, this is going to be capped by the 2n, right? D has to be smaller than 2n. They don't mention that anywhere, but that would make sense to me. Yeah, and seen as tuples collections. Yeah. So what was it? GLEV is a tuple of GLWE, and GGSW is a tuple of GLEV. I think that was the order. So this extends. Trivially, I guess. I believe that. I believe that. So TFHE dot product is still well, is that the multiplication then? Is that the multiplication? I don't understand. Is okay. Okay, let's read. But I'm wondering if it's a dot product between encrypted stuff, or it seems like we have a vector of a public elements, and so we're doing a dot product. It's just a linear combination, right? I don't think it's very useful to call it dot product here. I mean, maybe I'm being pedantic, or not pedantic, but like just weird, because I haven't seen this notation before. Getting used to notation and to other people's lingo is also good. A vector of LWE ciphertext and a vector of integers. So we're still not at the multiplication. We haven't, like, all of that is supposedly easy because it's all linear, and we still haven't looked at the multiplication or the bootstrap. All right, so let's go through that fast. Yeah, and maybe I don't like skipping things when I'm really trying to understand something, but I think it's okay to skip things about the noise because we're trying to understand things at like a medium level at this point. So we can always go back to understand the noise and how it's bounded, what's its distribution, things like that. Vector of ciphertext and vector of Scalar. I guess they explained for LWE, GLWE, okay. Why is out in LWE? That's interesting. Oh, okay. Right. No, not right. Isn't that weird? I'm not sure. Why would out be in LWE if we are in GLWE to start with? You think like CT is in GLWE and CTI is in LWE or something like that? Or RWE? Yeah, that doesn't make sense to me. So scalar modes of a GLWE and CX gives you a GLWE, right? And so an additional GLWE should give you a GLWE. And the proof is that we are definitely in RLWE because we see these X's. And presumably we might even, we should be in GLWE also. I don't know. I'm not going to try to understand too much of that. Okay. Subtraction, yeah, of course. That doesn't make sense to spend time here. Public key encryption. Should we look at that? That sounds like a big start. Let's look back at the. Is there a table of content here? All right. So we've been through the morphology of FHE ciphertext, which is interesting, right? Encoding Boolean and small integers. I guess we haven't really looked at that. Or I guess we haven't looked at that yet either. Oh, no, we have, right? Never mind. So yeah, the Lev was built on LWE. Lev is on top of LWE. GSW is on top of Lev. Okay. Key switching. Yeah, public key encryption. We're still in the simple version. Okay, so maybe we should see it. Where is the multiplication explained? External product, maybe that's a CMUX. Sounds interesting as well. Maybe that's what we should read. It's interesting that they don't talk about CBS. They only talk about programmable Bootstrap. Would love to have them talk about. They also, apparently, the programmable Bootstrap stuff uses lookup tables. So that's interesting. How do they do that? By the way, it's never a good idea to like look up ahead of time. It's discouraging in a way because there's so much to read. Arithmetic is going to be like you're building abstraction on top of abstraction, right? I'm guessing. But I'm trying to speedrun this thing. So I'm trying to figure out, okay, what should I read? So let me read a bit about CMUX. Let's make it interesting. Like, it's a puzzle. Then we'll come back. I mean, it's if or else, right? This is what we do in ZK. Beta is 0, then we get M0. Beta is 1, then we get M1. It's built on top of the external product. So we don't understand it yet. Can we talk about CBS? Oh, interesting. Wait, is that the same beta as the control, the selector bits? That doesn't make sense, right? Isn't GLEV... Let me just go back to that definition. That was the definition, right? We had this base. It's kind of weird that we're, you know. Oh no, this, so we have to go back to GGSW, and we have a minus SI. It's -1 by definition, you know. Never understood that part, but why is it not -1 suddenly? I don't know. That is weird. Does it make sense to you? No. That doesn't make sense to me yet. We just have to assume this is, you know, we got something like that, I guess. And we don't know how we got that. It's not even an encryption of beta, right? Oh shit, it is? Oh yeah, minus M, right? It's an encryption of M. Minus M is an encryption of M here, right? But why do you have the secret key? So it's an encryption of our bit selector, and part of our encryption key, and it's the same secret key that was used for the messages. All right, and it's repeated here. So why repeat the key here as well? This is really, really weird. We just do external so we purely do what we did plus CT0. So it is this formula. So that it's I mean, in ZK, that's what we would call a constraint. here it's not a constraint because that's we're actually computing this thing, trying to get the results. So I mean, it's a circuit. It's an arithmetic circuit in both ZK and actually in ZK and in PC and in FHE we use the same arithmetic circuit. So that's amazing. That makes a lot of sense at the same time. Just so easy, right? Like that's the CMUX and that's it. There's nothing else, as long as you understand the external product, right? And we understand the addition, we understand the subtraction. And of course, as you do all these things, you have to track the noise. And how you get this thing. It's interesting because here they call it GGSW of beta, but it's beta and S. Maybe they made a mistake here. I'm gonna assume they didn't make a mistake with the SI here, and it's me who doesn't understand something. And you would have to write the equations and go back to like how do they define these things. But complexity we don't care. The variance of the noise we don't care. We said we would skip these things. Blind rotate algorithm is one of the main building blocks of the PBS. By far most complex and costly part. Rotating is like multiplication by x of some power, right? Are we still calling that a rotation? So lookup table are used to do any computation, right? And in the bootstrapping algorithm, you want to use them for the decoding operation. Don't you want to use them for also the program, like the gate, like whatever you're doing as you're bootstrapping? Or are we just purely doing a bootstrap here? I thought PBS was like you do a bootstrap and you do an operation. But maybe I'm wrong here. You only do, I don't know. So this is 264. So we introduced PBS before in 2.6, right? Wait, we saw the sample extracts. Oh, we ignore it. I don't know why we ignored it. I thought it was related to subtraction, but it's not. Sample extract an operation taking as input a GLWE ciphertext and outputting an LWE ciphertext. So that's interesting. So you have a vector of polynomials and you're just gonna get one coefficient. So a vector of size 1, and instead of polynomial, it's just going to be a coefficient of a constant term, let's say. So what's the point? It's like a projection, like a flattened representation. I don't like that. They just give us the algorithm without explaining exactly what's going to happen. Informally, the sample extract consists in simply rearranging, possibly with negation, some of the coefficients in that vector You're encrypting one of the coefficients. Oh, so you're extracting one of the thing. A GLWE secret key is a bunch of, it's a vector where each element is a polynomial. Sure, yeah. That's what we said. So we have a GLWE ciphertext. And it's the encryption of a polynomial. That makes sense. An RLWE element. Does it make sense? I don't know. I'm getting very confused with all these representations. So I guess, yeah, so you obtain one of the coefficients. So yeah, you have the encryption of something, of a polynomial, and you just return one of the coefficients. All right. So it's kind of weird, right? Because GLW is itself a vector of polynomials, but you have to think that it also represents something, a message that itself is just a polynomial. So it's an encryption of a polynomial. So you're extracting one of its coefficients, right? And the alpha, I guess you can choose, but they say alpha is usually 0. They say it's somewhere else. The default being alpha equals 0, so you're extracting the constant term. We're not adding noise. And how does that work? So so we look at our vector, right? We have this GLW is a G, right? Whenever we have G is a vector. We look at this vector and sorry. It's a bit annoying because we're dealing with different things, right? We have an alpha, which is just an index. Oh, by the way, alpha is 0. We should just think alpha is 0. And if it's 0, we don't have to do that loop, right? It's going to be easy. So we replace. So this is a vector, right? Because of the G. Everything here is a vector. So this thing is a vector of polynomials. So you take the first one, 0. And you take, I'm guessing this is going to be like, it's a polynomial, so you're getting one of its coefficients. What is alpha minus j? Oh, 0 minus 0. All right. So first coefficient. You're getting basically we're going to go through these, this is a vector. We're going to go through all of its entries and we're going to extract the constant term. And where do we place that? We place that in, I would just move the constant term, I guess, here. And this loop is not going to exist, right? We don't do this loop. So we just move the constant term to this. And then we, yeah, that's it, right? Or so 1 times n. Oh, but n is like, no. What is n? This is tough, but n is the size of the vector. of these vectors, right? Because the entries of the secret key are also the same size of A, which goes up to N. So why do we do I is gonna go through that? Well, oh, there's a vector of size K here. Oh my god. Okay, we need to figure out what's the K, what's the N. So there's a number of secrets. So that makes sense. So we are going through a number of, because there's a number of secrets, there's the same number of masks, right? So we're gonna go through here, we're gonna go through all mask, and we're gonna extract each constant term of all these mask elements, and we're gonna put that we're gonna create a new right. It's just weird, right? Because basically what we're getting is indeed in LWE. So you have masks, a body, but these entries now are just in a ring. They're just constant terms, right? And basically we just increase the number of masks, and this means, right, we're K up to Kn minus 1, and this is why we have these weird things. Are we gonna have a bunch of zeros in between? I'm not sure. I need to think about that more. But what I'm not getting is that what is the secret key, right? What is S here? The secret key has increased in size, right? If we increase the number of masks. Yup, yeah, right. This is big. And what is that secret key, right? We don't do we know? Encrypted with yeah. Definition 11. Oh my god, where? Wait, definition 11 is right here. Okay. Oh, okay. So we're really flattening everything. So we take every coefficient, right? This is for example, S0 is the first entry, the first key, I guess. So, key is a vector, the first entry of that key. And then that's a polynomial. So you take the coefficients, you take the constant term, sorry, then the first coefficient, the second coefficient, whatever. So you're really flattening everything. So I'm not gonna, I hate thinking about, sums and stuff like that. What I'm guessing here is that we're trying to extract all the constant terms. And so let's think a bit more about that one, but I think we're wasting a lot of time here. That's not how you speedrun something, right? Yeah, so we are going to take that loop. I was kind of wrong, right? Because this is going to n. And so we extracted the constant term. And actually, if we were choosing different alpha, we would extract everything before that alpha, I guess. And then everything that comes after the constant term so we're going from 1 to n. Sorry. Sorry again. Oh, it's come as double sneezing. Oh, I'm sneezing from the mouth, so it's like coughing, but all right, so yeah, we're filling the other entry of our mask, right? We filled the first one with the constant term, and we need to fill the other ones. But for some reason, we're gonna negate the other ones. Am I understanding that correctly? And also, why don't we just take we're negating the other one, and then we're taking in reverse order, which is what I find weird. So basically, the constant term is the only one that's true. Everything before is also selected correctly, and then everything else is taken in reverse order. So, for example, if we were selecting alpha equals 3, we would take 0. Like this entry would be like of the first, we're only looking at this guy. We're taking first entry, second entry, third entry, fourth entry, 0, 1, 2, 3. And then if we go up to 8, then we'll go like we'll go like 8. All right. And then we'll go or like 7, 6, 5, 4. And we'll these will be the coefficients index that we're taking, and when we're negating them. This is so weird. I'm guessing it's going to be useful at some point. All right, let's go back to what we were looking at before we went back to the sample extracts. But it was kind of weird. Model switch, external product operations. I guess these are things we really didn't look at all. And the CMUX we just looked at. We fast forward. These algorithms are complex, but like we just spent, I don't know how long I've been recording for. Let's say I've been recording for an hour. For an hour, we learned a bunch of stuff. Maybe I'll stop here, and it's gonna take me a while to make a video, and maybe I'll record another video restarting from here. How do I even stop the recording?